Hello and welcome back to my computer vision channel. Today we'll talk about RT DETR or real-time DETR. So first let me say a couple of words about the model itself, about the history of DETRs, transformer-based object detectors. So for example, if we go to this Papers with Code COCO object detection benchmark, we can see that it used to be dominated by CNN-based models. And about CNN-based models, people usually complain that they are overcomplicated, they require non-maximum suppression, which is that thing that removes two predicted bounding boxes if we think that they are of the same object. And obviously that's not good because this is like primary thing people talk about in papers about transformer-based object detections, that the thing, this non-maximal suppression, should not be there. It's a heuristic. It means that we'll never detect two objects clamped together. Nevertheless, for a long time, CNNs dominated the benchmarks. And then you see models like Dino come out, so this is the previous state-of-the-art, then Encoder, which is again DETR-based, which finally say that, okay, we are better than CNNs in quality, and we are simpler in concept in some sense. But that was for basically accuracy. Now, what about speed? If we think about speed, and it's really important for applications like robotics, self-driving cars. And I think robotics is even harder because in a self-driving car, you can put like enormously big GPU that allows you to put your big transformer and do some detection. On a robot, especially a small robot, you can't really do that. So like embedded object detection, that's a whole new story. And RT DETR is actually the first model that takes a step in that direction, and boy is it good. So it's actually faster and better in accuracy than the previous CNN-based models like YOLO. If we go to the paper itself, the paper talks a little bit about like where the latency of the CNN models come from, and it turns out that actually a big chunk of latency might be non-maximum suppression in some cases. And so you actually need to take that into account in your benchmarks. And so they came up with this new benchmark for end-to-end object detection that takes everything into account. And this RT DETR, as we can see, is to the left and up from all the other models, which means that it's more accurate and it's faster at the same time, at least for this interval of the speeds that we're interested in. So obviously models like CoDETR will be way over here, so much better accuracy, much slower, but we're focusing on this real-time part of object detection. And as we'll see now, RT DETR basically takes in all the aspects developed in the previous models. So it's basically Dino with some things thrown away and changed, which means that we basically build this sturdy ship and we've built Dino that is really accurate, that is really robust, and now we need to make it faster. So we take RT DETR, which tries to, rework some parts of the model to not only look at the accuracy, but the speed as well. And this is the plan for today. So first we'll talk about the encoder. So probably the most changes happened in the transformer encoder part of the model. Then we'll look at query selection. That's the second thing that changed in RT DETR. Then we'll look at similarities to Dino. So like what are other parts of the model? How are they similar to Dino? And finally, the results. So let's start with the encoder. So first, a reminder of basic DETR architecture. So I have a lot of videos about that, about the original DETR, deformable DETR, DAP DETR, Dino, all of them, so you can check them out. So we'll not dig in too deep into that right now, but a basic reminder of how that looked like. So we get this image coming from over here. It is passed through a backbone. So in other models that might be transformer-based backbone, like VIT transformer or swing transformer, it might be a CNN-based backbone like ResNet. Obviously, in RT DETR case, we need backbone to be really fast, so I've only seen ResNet-based backbones here. So then we just flatten everything out to pass it to the encoder. Because we lose position information, after that we add this special positional encoding as an extra embedding. Then we do the transformer encoder, which outputs the same shape as we had, so it can still be represented as this image. We can unflatten it into its original size. And then we have the decoder. So we get queries from somewhere, and in case of DETR, they're just statically initialized learnable parameters. We get this side input from the encoder, and then we do the decoder, right? So, and the difference to the encoder is that in the encoder, each pixel can be seen as, each sequence element can be seen as transformed pixel of the original image. In the decoder, each sequence element can be seen as an expert that now queries the image, talks to other query experts, and detects the actual objects. And then we have the prediction heads. And the main component of the model is the Hungarian matching loss that solves the problem of, us having 300 predictions. So now, like, which of them do we match to the object, which of them are duplicates, and so on. And so this is done on the training step. So on the training step, we apply the Hungarian matching loss that makes sure that the model does not output duplicates. And then during inference, we can just trust the model and just take the prediction as is. Now, if we look at where the most compute is spent, or where a lot of compute is spent, that will be the encoder, because we get a lot of pixels from the backbone, and transformer encoder, the full self-attention, is quadratic to the sequence length, which means it's the fourth power of magnitude with respect to the actual age of the image. So the original DETR uses 20 by 20 backbone output, right? This is really small. This is the representation of a 20 by 20 image, and this is an enlarged version of it. So it's like really pixelated, really low resolution. So to be fair, each pixel here represents a lot of information. So it's an actual embedding with a lot of high-level concepts encoded into it. So it's not such a big problem for classification, for example. But then if we talk about detection, apart from knowing what high-level concepts are there in the pixel, we also need the precise position to draw these precise bounding boxes. So if we only draw on this 20 by 20 image, the actual accuracy will not be that good, especially for the small objects. In deformable DETR, we took a step further. So we said that we're changing the actual attention type used in the encoder. So deformable attention is now linear in complexity with respect to the sequence length, which means that we can allow ourselves now to take several levels of intermediate backbone output. So we'll have 20 by 20, 40 by 40, 80 by 80, and then just pass all of them into the encoder, process all of them in parallel, and get our high resolution bounding box predictions that now are more accurate. However, if you look at the actual complexity of operating on every level here, this is what you will see. So we are linear now, okay, but then 40 by 40 is 4 times bigger in terms of pixel count than 20 by 20. And then 80 by 80 is 4 times bigger, right? So even if you use linear complexity transformer, linear complexity deformable attention, you'd see that only 5% of the time is spent on this deeper semantic processed version of the image, and then 80% is spent on basically this high resolution but shallower semantic concept image. And the idea behind RT DETR encoder is that you can now basically decouple two things that's going on here. So in deformable DETR, you would have attention between this low resolution image to itself, between this low resolution to high resolution image, and then the high resolution image, and then between the high resolution image itself, and so on. So the idea of encoder in RT DETR is now to decouple interaction within level to this fusion between levels, right? So we can say that we are only going to do interaction, this transformer self-attention within this level. So it's not that big, 20 by 20. And then when we need this higher precision prediction for the bounding box, what we'll do is we'll fuse this level with higher resolution level, and we'll fuse using CNNs, because we don't need to basically access all the pieces of the image now, as we do in self-attention. We just need to look at, like, if we are detecting this bird, we just need to look at the area actually corresponding to that bird and look at the higher resolution version of that area. And CNNs are actually good at that. So CNNs are very local in the sort of area where they look at when they process information. So this is the first part of RT DETR encoder, the interaction part. So we take just the smallest version of the image, 20 by 20. We pass it through full self-attention. So we don't bother with linear complexity now. We don't use deformable attention. We just use the classical pairwise self-attention. And then we get this transformed version of that image where now every pixel has interacted with every other pixel, thus helping disambiguate some concepts that we might have seen on the image. And I depict it in green here. So next what we do is fusion. And it's done in this S shape. So basically S, when we first, in the backbone, we go up, and then we go down, and then up again. And the same concept is actually used in a lot of CNNs like YOLO and so on. So what is happening here is when we go down, we take this lower resolution image that passed through the encoder. We take this high resolution image directly from the backbone. We perform this fusion operation. The result of that is this, in this case, higher resolution version of the image that somehow merged the information between these two. And it's like twice the resolution. So we started in 20 by 20, then upscaled to 40 by 40. Then we do that again to get to 80 by 80. And then we go down. So we repeat this fusion process, but now downsampling towards lower resolution. And we get this extra couple of smaller images. And so these three guys here will be our encoder output. So we still get these three sets of levels as encoder output, so 20 by 20, 40 by 40, 80 by 80, but we have saved a lot of compute not performing any attention between pixels in these higher resolution images. One interesting question is, like, why do we have to go down and then to go up? So my version of this is that when we go down, we start with this green version of the image which had full pairwise interaction between all pixels, so it has now improved understanding of the concepts. And when we go down, we basically upscale it, allowing it to correct resolution mistakes and get this same processed improved understanding, but with higher resolution. And then when we go down, we basically achieve this downsampled version with corrected mistakes. So now basically this image now has interaction concepts into it, but it's a high resolution image. And then this image has this corrected pixel information as compared to this one, but now it's of the same size. And this is how one fusion block works. So again, we start with an image like 20 by 20 and 40 by 40, and then we merge them together. So how is that done? So first you take this small image, pass it through an upsampling operation, which yields you the bigger image. And this upsample is basically just enlarge the image and do the bilinear interpolation, exactly as it will happen if you would just sort of enlarge the image on your computer. So this is called bilinear interpolation, because you try to approximate the pixel values on this high resolution image, not taking into account any outside information. So as you can see on my slide, this image is the same size as this image, but it's more pixelated because of that. Then we concatenate them together along the embedding dimension. So this guy was embedding dimension 256, this one as well. And then we concat them together, so we get this 512 by 40 by 40 image. And then we pass that through a series of convolution blocks that basically fuse the information together, and we get this improved version of the picture. So you can think of this fusion, right? So for example, this 1v1 convolution, what does it do? It doesn't convolve neighboring pixels, so it just looks at one pixel. And in our case, this pixel has 512 coordinates. So two concatenated embeddings from two versions of the image, this one and this one. And then we perform one fully connected layer to get this 512 down to 256. So at this point, we have full interaction between all the coordinates here. So we get this 256 out, which already has this merged information from both image pixels. And this is the second version of the block that is now going up, where we have one processed image of high resolution, another processed image of lower resolution, and now we want to achieve this purple version of the image. So now the operation is almost the same, except that now we start with this high resolution image and downsample it to this smaller image, lower resolution image, using the same bilinear interpolation concept. And then we do the same. So we concat, perform some convolutions, get the result out. So once again, what just happened in the encoder, we take this backbone output, the 3 levels, and we perform this expensive attention operation only on the smallest version of the image, because this is enough. This image contains all the information from the previous image, apart from maybe specific pixel coordinates. And then we do inexpensive, cheap fusion operations using some convolutions to basically propagate this pixel information between levels, and we get out pretty much the same thing as we would have in DETR or deformable DETR, but we've saved a lot of compute. There are a couple of things that are really interesting in RT DETR that we'll not dig in too deep into right now, but I still want to mention that. So first of all, they did extensive ablation studies, and they found out that this decoupling of feature interaction and fusion actually increases accuracy as well as speed, right? So it is possible to come up with like maybe better state-of-the-art model that does this decoupling. That's an interesting concept to research in future papers. Another interesting thing that I was showing you in the fusion block is this rep-VGG model. So here it was in this convolutional part that does the fusion between the concatenated images. So this is the paper for rep-VGG. It's from 2021. So someone might remember VGG as this old model, pre-ResNet model, pre-residual. It was good at the time, but then it got completely replaced by ResNet, basically. So what this paper talks about is, well, let's take the actual speed of ResNet. And we'll see that, and the core concept behind ResNet is the residual connection that is not used in all models. And if you actually take a look at that from the speed perspective, from the actual speed of performing inference on the model, on the actual hardware that we have, we'll find out that it's not really effective because of these branching, because of access to different memory locations, and so on. So what they did in rep-VGG is they try to train similar model to ResNet with residual connections, with the sum operation and so on, and then convert that to something simpler like just rep-VGG, like VGG, basically just convolution after convolution after convolution, but have it do the same operation. And they call this structural reparametrization, where you basically just have one 3x3 convolution that you compute out of your ResNet using pure math. And through the magic of this pure math, you now get the faster operation, which performs the same. So this is quite cool, I think. I think this one deserves a video on its own, but we'll not stop on that too deep right now. And finally, another paper I'll mention is this path aggregation network. So PANET, path aggregation network, is basically one of the papers that talk about this U-shape architecture or S-shape architecture, and they basically propose these ways to propagate pixel information between levels and so on. They also talk about this importance of this short connection that basically allows this direct pixel information to travel to the levels, to the process level that you're interested in through the shortest path. And so this is why in the fusion block we have this basically skip connection that just comes through one 1v1 convolution to help preserve this shortness of path from the just raw pixels to your output. Now let's talk about query selection. So once again, a bit of history how it was happening in DETR. In DETR, there was no query selection. You just say that you have static queries that are not actually dependent on the image, and then you train them along with the model. And the result of that is basically that each query learns to specialize. So you might have queries that know how to detect birds in this upper left corner. You might have queries that learn how to detect cars here and here, for example, and so on and so forth. So they're just statically initialized, not dependent on the actual image content that you process right now. Then in deformable DETR, we perform query selection, which means that we take encoder output, and encoder output is basically a lot of pixels in the same shape as the original backbone output. And then you say that you want each pixel to output class prediction and bounding box prediction, the same as you would have for the decoder. And then you would select those predictions that have the highest probability. So what does that mean is that you have these lots and lots of queries. You only look at those queries that actually got selected, only they actually participate in the loss. And so for example, for one such query output, or sorry, one such pixel output, pixel prediction, we would have class predictions, right? So we have 80 classes like bird, cat, ball, car, no object, and so on. And each such output gets the probability. So we say that the probability that it's a bird is 0.73, then cat 0.57, and so on and so forth. And then we have the ground truth. And we get the ground truth for Hungarian matching. And so in this case, let's say that it is a bird. And the way it is encoded in the loss is one-hot encoding, which means that for the bird, we will say that we need 1 for that coordinate that corresponds to the bird, and then 0 for everything else. And that's how you train this classification branch for the decoder, for the encoder, and so on. So basically, since this is 1, it will push this bird prediction up and push everything else down in this case. And when we do query selection, we basically rely on this predicted probability to select those sequence outputs that are actually sure that they are detecting something, right? So some of them might detect no object. Some of them might detect some object, but have low confidence in that. So for example, this guy might also say that it's predicting a bird, but then the probability is just 0.26. So he'll probably not be the one to get selected for the query. But the problem here is that this predicted probability only talks about class, which means that this output can really be sure that it's a bird, but have no idea where it is. So it doesn't take this bounding box error into account. And that is what's solved in RT DETR. So in RT DETR, it's called uncertainty minimal query selection. And this is how it works. So we also have the same class predictions, so one number per each of 80 classes, but the ground truth is now different. So we also say that we got matched with the bird, and let's say that the actual prediction, so this is the ground truth, and the actual prediction of the bounding boxes is now a little bit off. And instead of putting 1 in here, we put IU between predicted bounding box and the ground truth bounding box, which is 0.77 in this case. And then we let the model try to predict that. So now this still sort of pushes this prediction up, this prediction down, and so on. But now this prediction of confidence not only takes into account the actual confidence of your predicted class, but also your confidence in that the bounding box that you're predicting is correct. So this basically helps generate better queries. Now let's quickly talk about other parts of the model and similarities to Dino. So we also use extra denoising objective in the decoder, which means that we don't just rely on this Hungarian matching loss during training. We also have this extra queries generated and extra objective for denoising queries to help stabilize and speed up the training. We also use deformable attention in the decoder. So we didn't bother with it in the encoder because we only looked at 20 by 20 image. In the decoder, we have this entire encoder output 3 levels as the side input. And for cross attention between queries and that side input, we use deformable attention. And for that, we also use reference points, as is typical in deformable attention, which we get from our special query proposals that we've talked about, and they also updated layer by layer, as in RT DETR. So all of that is basically using all the state-of-the-art concept that we know in the field. And now let's quickly talk about results. So this one we already talked about. If we actually plot the accuracy versus latency trade-off, we can see that RT DETR is to the up and left. So for any given latency that you have, if you switch to RT DETR, you'd have better accuracy. This is a more detailed table of the results. So here, for example, we can see that if we look at those Dino models that use ResNet as a backbone, you actually improve accuracy, right? So this RT DETR R50 backbone model is something like 2.2% better accuracy, 20 times better requests per second, so it's 20 times faster, like half the gigaflops of the model. So it's really better in all accounts as compared to like previous transformer-based object detectors. Now, unfortunately, we don't see any RT DETR variants with more complex backbones like VAT transformer or swing transformer. I don't know whether it is because they didn't try or because they tried and that didn't work as well. What you can also see from here is that compared to YOLOs, now the improvement is not that great. So for example, this YOLO V8X, 53.9 accuracy, that's slightly better than here in half the speed. And YOLOs sometimes are actually better on smaller objects. So this AP-val small measures subset of accuracies computed over small objects only. And you can see that RT DETR still loses in that accuracy as compared to YOLO. Nevertheless, it's a first transformer real-time model, a huge advancement, and I want to say that it's also much simpler to work with. So traditionally, my next video will be about reading the source code, and the source code is just really, really simple as compared to the previous models. And so you don't need to install like custom codec kernels. You can convert it to anything you like. You can use it to do inference on your embedded devices, and if it fits, of course, and so on and so forth. So this is really cool. A lot of work was done just to make sure you can actually use that model in your project. It is still better accuracy to speed trade-off than YOLOs. And it also has interesting finds regarding accuracy. So like decoupling that increases accuracy, the fact that with the same backbone, RT DETR is actually better than Dino, for example. That basically indicates that concept that we've just discussed might actually improve state-of-the-art of accuracy, not just speed. So this is really interesting. This is it for today. Thank you everyone for listening. I hope that it was useful, and see you soon.